Good morning. I'm Dr. Niti Maheshwari, Assistant Professor, Ajay Kumar Garg Engineering College, Ghaziabad. Today, I'm going to deliver a lecture on nanomaterials and its application. Now, this topic is related to engineering chemistry, code being KS102T and 202T. Now, coming first to what exactly we mean by the term nanomaterials. Nanomaterials are those materials whose size is of the order of on the nanoscale. Nanoscale means of the order of 10 to the power minus 9. And the applications of these nanomaterials in the latest technologies is termed as nanotechnology. So, nanotechnology is the science and technology of small things. And this nanotechnology, it is one of the most rapidly advancing scientific technologies for today. And as you can see, a nanometer is 1 billionth of a meter. That is 1 nanometer, it is equal to 10 to the power minus 9 meter. Next, coming to any material, it can be manipulated at the scale of nanometer. That material is known as nanomaterial. So, when we break down a bulk material to a small size of the order of 1 to 100 nanometer, that material is termed as nanomaterial. So, in nanotechnology, a nanoparticle is defined as a small object that behaves in itself as a whole unit. And its size, it ranges between 1 nanometer to 100 nanometer. And these nanomaterials, they can be made from either metals, or they can be made from ceramics, or from the minerals, or from the polymeric materials, or they can also be composites or the carbon allotropes, for example, fullerene. Now, when we break down the material to the nano size, a lot of surprising changes have been noticed. For example, an opaque substance, it can become transparent, and the example of one such material is copper. When the material is opaque, or when you say it is in the bulk form, it is solid, it is opaque, light cannot pass through it. But when you break down to a smaller size, it can become transparent. It will allow light to pass exactly between it. Or the inert materials, it can become a catalyst, for example, platinum. Stable materials, they can become combustible, for example, aluminium. Aluminium is highly stable when in the bulk form, but when we break down into the nano size, it becomes combustible. Solid materials, they can turn into liquid at room temperature, for example, gold. Gold, we all know, is proper solid at room temperature, but when we break down to the nano size, that is of the order of 10 to the power minus 9, it turns liquid even at the room temperature, or it exists in the liquid form even at the room temperature. Insulators, they can become conductors, and vice versa. The conductors, they can also become insulators. For example, the carbon nanotubes. Now, the question arises, why the properties of these nanomaterials, they differ significantly from the other materials? What is the basic reason behind the property change from the bulk to the nano size? Now, the first basic reason of change of the properties is when we break down the bulk into the nano size, the ratio of surface to volume, it increases significantly. Now, here I am taking one example how the ratio changes. Now, the surface to volume ratio, here you can see I have taken a cube of 2 by 2 inches. So, the volume of this cube is 8 cubic inches, whereas the surface area is 24 square inches. And surface to volume ratio, here you can say it is 3. But when we break down into exactly half, The volume is 1 cubic inch, but the surface area is 6 square inches. And the surface to volume ratio is of the order of 6:1, that is 6. So, the surface to volume ratio increases by reducing the size. So, one of the major reasons for the change in properties is the increase in surface to volume ratio. Now, the nanoparticles, they have very large surface to volume ratio than the bulk materials. Thus, it makes nanoparticle more chemically reactive, and therefore it affects their strength and properties. What happens when I break a bulk material to the nano size? When the material is in the bulk state, you can see the particles on the surface, their number is lesser in comparison to the particles which are present inside. But when we break down the material to a smaller size, the grain size also reduces. Grain size means the particle size also reduces. As a result of increase in the surface area, more number of particles, they are going to be present at the surface, or they are going to get exposed and they are going to be present at the surface. So, the properties which are derived from the size of the particles, they are going to increase multiple times. For example, if a material, it is showing ordered electronic spins at the surface and disordered electronic spins inside the bulk material, but when I break down this material to a smaller size, the particles which are going to be present on the surface, it is going to increase. That means the number of ordered electronic spins is also going to increase, whereas the number of disordered electronic spins is going to decrease. So, the properties which can be derived from this ordered electronic spins, for example, magnetic properties, they are going to increase. If a material is not magnetic and the bulk size, but it can show magnetic properties when we break down to the nanoparticle size. Second effect which is seen is the quantum effects. It begins to dominate the behavior of the matter at nanoscale, and it is shown by the term quantum confinement. Now, we all know that the energy gap in semiconductor is proportional to the inverse of the square of its size. That means when we break down the particle to a small size, the energy gap between the valence and the conduction bands, it start increasing. As in the bulk materials, the valence band and the conduction band, they generally overlap. That means this gives rise to the continuous bands in the bulk material. But when I break down the particle to a small size or the material to the small size, instead of these continuous bands, discrete energy bands are formed. That means there is an energy difference between the valence and the conduction bands, and only specific transitions are allowed which are specific to different wavelengths. So, therefore, the properties of the nanomaterial is going to change, and this confining the particles to a one energy level, it is known as the quantum confinement. Now, coming to the classification of nanomaterials on the basis of their rectangular size. Now, these nanostructures, they can be divided into three. For example, this is the bulk material, the second one is the quantum well, third one is the quantum wire, and the last one is the quantum dot. So, depending upon the material in which dimensions we are converting into the nano size, this classification is given. Now, coming to the quantum well, In case of quantum well, if only one dimension of the material, it is reduced to a nano range, while the other two dimensions, they are large. Now here you can see that only in one dimension we are converting it into the nano size, but the other two dimensions of the material is large. So such material are termed as quantum well. They are also known as the potential wells, and we confine the material into a planar structure rather than in the three-dimensional structure. Second is the quantum wire. If we convert the bulk material into the nano size, where the two dimensions, here you can see that the two dimensions are of the nano size, but one dimension is large, then it is known as the quantum wire. And last is the quantum dot. If we break down the bulk material in all its three dimensions, or brings the bulk material to a nano size in all the three dimensions, then it is termed as the quantum dots. And these quantum dots, they are utilized in the photodynamic therapy for the treatment of cancer. Coming to the properties of the nanomaterials, by only varying the particle size, the properties like melting point or the solubility or the transparency or the catalytic properties, they are going to change. When we break down the particle size into a smaller size, then you can see the edges, the points and the edges, their number is going to increase. As a result, there is going to be enhancement in the catalytic properties of the material, and with different surface properties also of the nanomaterials. For example, dispersibility, for example, again, catalytic behavior or the optical property changes. These properties will also change on breaking down the bulk material to the nano size. Another reason, again, which I have already discussed, is due to the large surface to volume ratio. The number of reactive sites, it is going to increase. As a result, their catalytic activity will also get enhanced. Coming to the approaches for the preparation of nanomaterials. There are two approaches for the preparation of nanomaterials. One is the top-down approach and the other one is the bottom-up approach. Coming first to the top-down approach. In the top-down approach, this approach involves of breaking down the bulk material to the nano size. So, this process involves the production of very small structures from the larger ones or the larger pieces of the material. For example, it involves the mechanical crushing of the solids and breaking down into the nano size or the nano powder. Now, this approach is expensive. Why? Because lot of the material gets wasted. This material is synthesized when by the repeated pattern transfer. We make a pattern on the bulk material and break down the bulk material to the smaller size. Again, the pattern transfer till we reach the nano size. So, on the repeated pattern transfer, the material is going to get lost. The example of such type of the approaches is the etching or the lithography. The second important approach is the bottom-up approach. In this approach, we generally start with individual atoms or molecules, and we build these atoms or molecules into larger structures. And this is to allow atom or molecules to arrange themselves to a nanostructure. We allow these atoms and molecules to arrange themselves, to aggregate, arrange themselves till they become of the nano size. Since we are starting from individual atoms or molecules, this approach is comparatively less expensive. Example is the ion implantation, molecular self-assembly, chemical vapor deposition. Now here, I am showing the two approaches. This one is the top-down approach, where this is the bottom-up approach. Now in the top-down approach, we are starting from the bulk material, converting into the smaller size and repeating the patterns, and then finally captivating the particles when they are of the nano size. In the second stage, or in the second process, we start with the individual atoms. We allow their clusters to be formed, and finally these clusters, they build up to the nanoparticle size. And the methods that are using top-down methods, I've already discussed, mechanical grinding or the erosion methods. The bottom-up approach, it is the aerosol technology or the chemical precipitation or the self-assembly. Coming to the examples of nanomaterials. The first example that I'm going to take is the carbon nanotubes. Now these carbon nanotubes, they are made up of sheets of graphene which are rolled up to make a tube of 0.4 nanometer in diameter. Now what exactly is graphene? You have already studied the structure of graphite. If we take a single layered graphite, this is a single layered graphite structure. This single layered graphite is known as graphene, and it is quite a thin structure. When we roll this in the form of a tube, then it is known as carbon nanotubes, and they are hollow from inside. Now depending upon the number of sheets we are allowed to form a carbon nanotube, these carbon nanotubes can be of either single walled carbon nanotubes or the multi-walled carbon nanotubes. These carbon nanotubes, they can be conducting, or they can be semiconducting, or they can be insulating in nature, depending upon how we are going to roll the sheet around. The pattern of the sheet, rolling the sheet, will decide whether the CNT tubes which are being formed are the conducting, semiconducting, or insulating in nature. These carbon nanotubes, they possess high tensile strength, and they are stable up to very high temperatures for of the order of around 2800 degree centigrade. The second example of nanomaterials that I am going to take is fullerene. Buckminster Fuller was the one who discovered fullerenes, and these fullerenes, they are prepared by vaporizing a graphite rod in an helium atmosphere, or you can say in the inert atmosphere. And these fullerenes, they are made up of pentagons and hexagons, where no two pentagons are going to share a sides. No two pentagons will share the sides. So these fullerenes, they have, the most important is C60. It is going to have 60 vertices, and a carbon atom will be present at each vertex. Now in this case, this C60, it has 32 faces. Such faces, the number of such faces is 32, out of which 20 are going to be hexagonal and 12 are pentagonal. And I have already said the pentagons, they are not going to share a common side. So these fullerenes, they have certain advantage properties also, you can say. They are not soluble in water. And this fullerene, under normal conditions, it is impervious to almost all the substances. But since this fullerene, it has a cage-like structure, it can help in the transfer of the drugs, or they can transfer the drugs to the body. So these fullerenes, they belong to a class of cage-like carbon compounds, and they are composed of fused pentagonal and hexagonal sp2 hybridized carbon rings. So they can be utilized as the drug carriers. And this fullerene, it has also found to be useful against fighting the AIDS. Coming to the applications of nanomaterials, there are various applications of nanomaterials. These nanomaterials, they can be used in optical engineering. They can be used in defense and security. The fullerenes, as I've already said, it is also impervious. It does not allow the laser light to pass through it. So this fullerene, it can be used in the future warfare. The nanomaterials, they are also being utilized in bioengineering, in the field of commerce, in the field of nanofabrics, for the preparation of nanofabrics. The sportswear which are being synthesized these days, they are the nanofabrics, because those materials, they contain a lot of shine, and that is because of the nano size of the material. They can be used in the energy, in medicines and drugs. The home pregnancy kits, it contains the carbon nanoparticles. They are utilized in the nanotechnology, in the nano devices. Some of the examples which I have taken: the nano-sized titanium oxide and zinc oxide, they are being used in sunscreens as they absorb ultraviolet radiations. Similarly, the silver nanoparticles, they are also being utilized as the antibacterial agents. The nanotechnology produces more efficient, lightweight and high energy density batteries. Nanomaterials, they are also being used in the drug delivery system. As I've already said, fullerene is one example. Nano coatings, they improve the properties like wear resistance and scratch resistance and hydrophobic properties of the materials. So the by applying the nano coating, the material becomes wear and tear resistant, and it also it is insoluble or does not allow water to stand over it. Nanomagnetic materials, they are used for large amount of data storage devices. So the data storage devices, they are made up of the nanomagnetic materials. Nanostructured membranes, they are being used for the water purification techniques. Coming to some of the questions, the first question that I have is the nanoscience. It deals with the material whose size ranges from. The correct answer is B. The nanomaterials are those materials whose size is of the order of ranging from 1 to 100 nanometers. The second question, nanomaterials, they differ from bulk materials, whether in the electrical properties or the magnetic properties or the optical properties. The answer is all of the above, because on breaking down the bulk material to the smaller size, all the properties of the material, they make a huge change. The carbon nanotubes, they are considered as 0-dimension structures or the 1-dimension or the 2-dimension or the 3-dimension structures. The carbon nanotubes, in that case, it is 1-dimension structure, because we break down only in 1 dimension to the nano size. The other two sizes are large enough. Which is not the example of the bottom-up approach for the synthesis of nanomaterials. The bottom-up approach is starting from the atoms and then building up the large structures up to the order of the nano size. In this case, the mechanical grinding is the top-down approach. Which of the following is not a 1-dimension material? Carbon nanotubes, I've already said it is 1 dimension. Nanowires, again 1 dimension. Nanocones. Nanocones are not 1-dimension materials. Next, a layered structure of pentagons, hexagons and heptagons. It can be rolled like CNTs, and the name of this structure is halides. Nanomaterials are used in medicines as, they can be used as drug carriers, they can be used for the diagnosis, they can be used for the treatment of the illness. The answer is all of the above. We can utilize nanomaterials for all these. Nanomaterials are used to improve performance of the tires, for lubrication, in data storage devices as the computer hard disk, or all of the above. Again, the answer is all the above. Dash they are going to find use in food packaging as they are capable of changing color when the food is no longer edible. Nanosensors are being utilized to study whether the food is fresh or it is stale, or whether we can eat the food or it is not edible. So the answer is nanosensors. In the surface nanoengineering, glass surfaces are coated with which material? Nanoparticles make the glass hydrophilic rather than hydrophobic. The answer is titanium oxide. When we coat the nanoengineering glass surface by titanium oxide, it makes the glass hydrophilic instead of hydrophobic. Thank you.